afternoon, Mr. Chairman, ladies and gentlemen. My name is Chun-Hua. I come from the Southeast University in China. My presentation is about high-performance post-silicon interdigital capacitive temperature sensor based on graphene oxide. My presentation is divided into 5 parts. First is introduction. I will talk briefly about the motivation of our research. Then, the fabrication of the post-silicon temperature sensor will be given. After that, the structure of the temperature sensor will be shown. The result and discussion, and last is the conclusion. First is the introduction. As we all know, temperature sensors have been used in various areas, such as meteorology, agriculture, industrial control, medical instrument, and so on. With the maturity of MEMS technology, the temperature sensor have been small and small. So we can see that the left one is a capacitive temperature sensor, which can be used in the range of temperature of negative 70 degrees centigrade. It is very hard for integrated circuit temperature sensor. Then the middle one is also capacitive temperature sensor. It was fabricated by surface micromachining, and this temperature sensor can be used in the range of more than 100 degrees centigrade. And the large one is the PT resistance temperature sensor. This temperature sensor is always used in the multi-MEMS sensors. For example, it can be used for temperature consumption of other sensors. The key factors of MEMS temperature sensor is the electrical interconnections, power dissipation, and the cost of package. Graphene oxide, due to the oxygen functional groups of graphene oxide, graphene oxide have been used in many areas, such as they were used in humidity sensors. By use the graphene oxide as a sensor material of the capacitive humidity sensor, the capacitance, the sensitivity of the humidity sensor can be enlarged very much. Then also the dielectric constant of graphene oxide variation with the temperature. In this figure, we can see that the dielectric constant of graphene oxide increases exponentially when the temperature increases linearly. So we designed a post-silicon temperature sensor that uses the graphene oxide as a sensor material. The graphene oxide was used to fill the capacitor dielectrics. When the temperature increases, the dielectric constant increases exponentially, so the capacitance between the post-silicon electrodes can increase too. Now I will introduce the fabrication of a post-silicon temperature sensor. To achieve the electrical interconnection and the wafer packaging of the temperature sensor, we use the wafer bonding technology. A lot of bonding technology have been researched in recent years. For example, the analytical bonding technology. The temperature is between 300 degrees centigrade to 450 degrees centigrade, and the bonding stress is very high. But this process needs very high voltage. Maybe so it is impossible for it to be used in the post-CMOS MEMOS. Next is the fusion bonding technology. The temperature is up to 1100 degrees centigrade, so it is also can be used in post-CMOS process. For the temperature is too high, the aluminum of the IC integrated circuit can not achieve. Next will be the gold-gold bonding technology. The gold-gold bonding technology, the temperature is about 400 degrees centigrade, and the bonding stress is higher. Compared, what is more important? Compared with these two bonding technologies, the gold bonding technology can be compatible with the standard aluminum metallization of CMOS process. So we use the gold-gold bonding technology to achieve the electrode interconnection and the vapor packaging. This is the bonding stress test structure. First, the gold is spotted on the glass wafer, and the gold is spotted on the silicon substrate. After that, the gas chipper was flipped on the silicon wafer. After the bonding stress, the shear strength is more than 50 million Pascal. Now I will talk about the fabrication of the temperature sensor. First, a shallow graph was fabricated on the silicon wafer by dry etching process, such as the reactive iron etching process. Then, the gold was spotted on the silicon substrate and the glass wafer. After that, the glass wafer was flip-chipped on the silicon substrate by gold-gold bonding process. The wafer was thinned to about 40 micrometers through chemical-mechanical planarization process, and the indicator electrodes were released through ICP process, which is the deep reactive iron process. At last, the graphene oxide is dropped into the gap between the indicator electrodes. The graphene oxide we used in our work is made by a modified humorous method. First, as shown in this figure, 14.6 milligram graphene oxide was exploded in the diluted water, and then it was ultrasonication. It was exploded in the diluted water by ultrasonication. After that, the graphene oxide dispersion was fabricated. Then it was dipped into the gap between the indicator electrodes, and the solution was dried at a temperature 45 degrees centigrade for 2 hours. The temperature must be low. For the high temperature can decompose the graphene oxide. Then injects the structure of the temperature sensor. The bond silicon temperature sensor contains 42 interdigital fingers, and the gap between the two fingers is 10 micrometers. The length of the overlap, overlap segment is about 200 micrometers, and the thickness of the electrode plane is around 36 micrometers. This is for humidity, we manufacture the capacitance of the temperature sensor. We designed this can to exclude the humidity factor. As shown in this picture, the temperature sensor was put in this can, and the nitrogen gas flow in this hole and flow out in this hole. By using nitrogen gas as a protective gas, the humidity together with its effect on the sensor can be reduced as much as possible. Now, this is the SEM photos of the temperature sensor. The graphene oxide was filled in the gap between the two fingers, and this is the SEM photos of the graphene oxide on the silicon, on the surface of the silicon. This is the sensitivity measurement of the temperature sensor. As shown in this figure, when the capacitive, when the temperature is same, the higher test frequency is the lower capacitive, and the capacitance of the temperature sensor increases exponentially when the temperature increases from negative 70 degrees centigrade to 40 degrees centigrade. And what is strange is that when the temperature increases from 40 degrees centigrade to 50 degrees centigrade, the capacitance of the sensor decreases rapidly. Maybe it is some oxygen group some oxygen functional groups decomposed of the temperature decomposed. This is the hysteresis measurement of the temperature sensor. Also, when the capacitance of the temperature sensor increases exponentially when the temperature increases from negative 70 degrees centigrade to 40 degrees centigrade, and it decreases rapidly when the temperature increases from 40 degrees centigrade to 50 centigrade. And this is the repeatability of the measurement. And the test frequency of these two results is 100 Hertz. Congratulations. A bunker silicon integrated capacitive temperature sensor based on graphene oxide was presented, and by nitrogen as a protective gas, the humidity together with its effect on the sensor is reduced, and the sensitivity of the sensor was improved significantly by using graphene oxide as the sensor material, and this temperature sensor can operate in the range of negative 70 degrees centigrade to 40 degrees centigrade, and the hysteresis of repeatability measurement of the temperature sensor was also given. That's all. Thank you for your attention.